Hey guys, this is Nurul Huda and I am an educator at an online learning app that is Unacademy. There also I am posting videos which are going to be very helpful for you for your CSI net preparation. So if you are enjoying my videos, if you are liking my teaching skills on YouTube, then I hope you will also like my videos on Unacademy as well. So follow me over there so that you don't miss out anything which I am posting there for your preparation of CSI net. So how you have to do this is just download this Unacademy learning app from the app store, and you have to search for my name, that is Nurul Huda, in the search bar, and you will get a screen like this which is shown on your screen right now, and you just have to click on this follow button to follow me over there. All right, and if you follow me, whenever I will upload a new video or anything, you will get notification for that. Secondly, you can also go over there, go to my profile directly from the link given in the description. So that's all for this. Let's continue with the video.
Hey guys, hello everyone. So welcome to the channel. So this video I was delaying till since long, and today I'm going to make this video. And this video is going to be about certain tricks and certain tips and tricks to find number of geometrical isomer, and we'll try to find out number of optical isomers. Basically, we will see that whether the molecule is optically active or not. So certain questions have been asked from here, that is to find out that whether your molecule or the compound given is optically active or not. So we'll see those questions as well from CSI net exam. So first we'll first understand the concept, and then we'll go to the question in the end of the video. Okay, so first of all, let's try to find out for the geometrical isomer. Now, what is geometrical isomer? Geometrical isomer means if you change the ligand, like if you have certain complex, and in the stereo of that, means in the space, if you change the position of the ligand, and if you get like some different complex, that means if the angles between the ligands can be changed, then that result into a geometrical isomer, that result into another isomer that will be having same molecular formula but different arrangement in space, and that is called your geometrical isomer. So basically, geometrical isomers are of two kinds, that is cis and trans. And optical isomers are what? Optical isomers are like when you pass a plane polarized light to a certain complex or sample, and when the sample it tries to turn the plane polarized light towards left or right, depending upon the nature of the sample, and you will get the polarized light to be shifted towards left or right. So depending upon that, we name it as a D or L form. So those are things for optical isomerism, but the main thing is the number of geometrical isomers, to find out the number of geometrical isomers. So I'll share some tricks with you. I'll not be going into the into the usual form of solving the questions. I'll just solve them with the help of tricks. So first of all, we'll take the example of tetrahedral complex. So for tetrahedral complex, I have a complex over here where we have metal, and it is attached to 4 different ligands that are named as A, B, C, and D. Now we all know that for tetrahedral complex, the angle between them is 109 degree and 27 minutes. Now for all of the ligands, between all of the ligands, the angle will be same. All right. So if you change the position of certain ligands, then also nothing will happen to the complex. The angles will be same, so there will be no change in the angles. So that's why the tetrahedral complex does not have geometrical isomer. So it does not have any geometrical isomer. Okay. Now let's talk about the square planar complexes. Now in case of a square planar complex, I have taken few examples, that is MA4, MA3B, MA2B2, MABCD. So these the letters represented in the small letters, small letters are the ligands, and this M is the representing your metal. So for MA4, if I draw the ligands like this, so 4A connected to metal. So if you change any of the A, like any of the location of it, nothing will be happening to the complex. The complex will be eventually remain same. Now I'll talk about this one because I want to show you that how isomerism works. So I can draw this like in two ways. I have 2A, so I can write them like this, and 2B I can write them like that. Or I have one more way of writing them, or I can write them like this, that I can make A and B. So what has happened over here, if you'll see, the angle between those two same ligands, that is B, is 90 degree over here, whereas in this complex the angle between 2B is 180 degree. So it means the angle between the ligands have been changed. That means these two complexes, these two structures are geometrically like isomer of both each other, whereas the molecular formula and other things are same, just the angle between the two angle between the two ligands is changed in both of them. So that's why we'll call it a geometrical isomer of each other. All right, now I'll share the trick how to use this trick. So what you have to do, you just have to pair up the ligands which are given in the question, and you have to see then in how many ways you can pair it up. So if you have Ma4, so we can pair it up like a all right, and there is no other way of pairing it up. So that means there is just one way of pairing it up. That means you just have one structure, you cannot have the geometrical isomer of that. So if somebody asks that if you have geometrical isomer of that, so you will say no, I have just one structure of the complex and there is no other structure which could be done so that we can get a geometrical isomer of that. Now if I talk about this, so only talking about the ligands, if you try to pair them up, so how you can write, you have 3a and 1b, so you can pair 2a and b like this, and you can not like you do not have any other way of pairing it up. So you just have this way or this way. So just two ways of pairing the atoms. So here also you don't get any geometrical isomers. All right, whereas in this case where I have discussed structures, if you try to find it out, if you try to find the structures using the trick, so how you will do, you have like 2a, so you can pair them like this, aa, and 2b, you can pair them like this, aa bb, or you can pair them like this, ab ab. So there are two structures, two ways of pairing them up. So that's why if you somebody asks you that how many geometrical isomers you have, so you will say you have a complex which is having one geometrical isomer of it. So you have two structures which are geometrically isomer of each other. Now let's talk about ABCD. So in how many ways you can pair this ABCD? So you can pair it like ABCD like this, or ACBD like this, or AD and BC. So there is no other way of pairing it again in any other way. So how many geometrical isomers here you will get? You will get 3 geometrical isomers. So in this way you just have to find it out, what you just have to pair them up and just try to find the number of ways in which you can pair up, and you get the answer of how many that compound will possess. Okay. All right, so now if you want to find out the optically activity, like if you want to find it out that whether the complex is optically active or not, then what you have to do, the rule says, the trick says that the complex that it should not have same ligand like AA. The pair of the ligand should not be like same, that is AA BB, it should not be there in the complex. And one more thing, that it should not have repeating pairs like AB AB, it should not be like that. So if the complex is having repeating pairs, then also it is optically inactive, and if the complex is having like same ligand repeating in one pair, then also it will be optically inactive. All right. So based on this rule, if you want to check that whether which of the complexes of yours is optically active and which is inactive, so if I talk about the first one, here we have repeating like the A is there, so that's why it is optically inactive. All right, so I'll just write it OI, means optically inactive. Okay, now over here you can see that here also we have one repeating ligand over here in the pair, so this is also optically inactive. And if I talk about this pair, so here we have repeating one, so optically inactive here also. And in this case we have not non-repeating inside the bracket, but this is a repeating pair. All right, so this is the second fact, that is you should not have repeating pair, so that's why it is also optically inactive. So both of them are optically inactive. But if I talk about these, so here if you will see, so there is like the ligands inside the bracket are not repeating, as well as the pair is also non-repeating, so optically active. So it is also optically active, it is also optically active, and this one is also optically active. So all three are optically active. So you will be having 3 geometrical isomers, and for all 3 geometrical isomers you will be having one D form and one L form. So one of them will be same. So overall stereoisomers, if somebody asks, so there will be 3 geometrical isomers and 3 optical isomers. Why 3 optical isomers? Because one of them are these, and other one will, like if this is the D form, then other one will be its L form. Now again, if it will be your like let's say it's L form, then other one will be its D form. So you will just get one another form of it. So that means 3 more you will get due to the optical activity. So overall stereoisomers for this complex, for this set, for MABCD, you will get 6. Okay, I hope you people understand this thing what I am telling. Okay, now let's talk about the those octahedral complexes. All right. Okay, so let's talk about the octahedral complexes. So I'll just, the rules are same, everything will be same, just I'll take few examples and I'll try to explain you guys. So let's take example of Ma4B2 type of complexes. So in Ma4B2 type complex, if you make the pair of the ligands, you will find that you have 4A and 2B. So how you can pair it up? You can pair it up like AA, and BB, or how you can do it? You can pair it like AA, AB, and AB. Okay, so this is one more way, and there is no other way. If you try to, like, if you want to try, you can try in others way also, but there is no other way, no other different way. If you feel like you can make AB, AA, AB, then that will be identical. So their positions doesn't matter. You can, like, you cannot switch them. Okay, the positions are not doesn't matter. Just the pairing should be like unique. All right, so here you are having two geometrical isomers, and if I talk about like geometrical isomers will be two. So one pair, and or like one way of arrangement and second way of arrangement. And if I ask you how many are these optically active or not, so first one will be optically inactive. Why? Because the ligands are pair over here, and here also we have one of the pair, so that's why it is optically inactive. Let's talk about this Ma3B3. So how you can pair them? If you have 3A and 3B, so you can pair it like AA, then AB, and then BB. One of the way is this, or you can pair them like this: AB, AB, and AB. Okay, now I don't think there is another way of pairing it up. All right, so there are just two ways of pairing these complexes. So number of geometrical isomers over here will be 2. Okay, and if I ask are they optically active or not, so for the first one they are optically inactive because you have the same like unit repeating inside, and for the second one also it is optically inactive because you have the pairs are same, so identical pairs are there, so that's why it is optically inactive. So in octahedral also you just have to see that whether two of them are same or not, just you have to see the two of them. Now we'll talk about Ma2, B2, C2. So for them, how you can repeat, how you can write the combination. So it could be like AA, BB, CC. Okay, this is the first way. Then you can write AB, AB, and CC. All right. Then keep AA like that only. Then you can write BC, BC, and then just keep the B1 like that. So AC, BB. So these are certain ways of like writing them. So how many geometrical isomers you will get? I think these are enough. Okay, so try to find if there are more ways or not. So I am just for now I am just like there are just 4 ways of writing them. So there will be 4 geometrical isomers for this. Okay, now if I ask you that are they optically active or not? So for the first one, these are optically inactive because you have repeating ligands inside the pair, and for the second one also you have optically inactive because you have repeating pair. For the third one also it is optically inactive because you have repeating pair over here as well, and fourth one also it is optically inactive because you have repeating pair here also. All right, now for Ma5B, how you will pair it up? So you have 5A, so you have AA, then AB, just like that. So you cannot like make more of it, so you just have one structure. So this is how many geometrical isomers? So it does not have any geometrical isomers, so it does not possess geometrical isomers. And is it optically active or not? So what we will say that it is optically inactive because you have same pair repeating over here. All right, so this was for your tetrahedral or octahedral and your square planar complexes having monodentate ligands. Now if the ligand is changed, that is if the ligand becomes bidentate, then also you can find out that whether your complex is having like if whether your complex will be optically active or not, and you can also tell that whether it will be possessing any geometrical isomers or not. So we'll try to find that also. All right, so let's just talk about the bidentate ligands. Okay, so bidentate ligands are of two kinds. There are two types. One are symmetrical bidentate ligands, whereas some are unsymmetrical bidentate ligands. Now what are symmetrical bidentate ligands? they're like, I'll represent them with this A, capital A, and their example is like ethylene diamine. Okay, so these are the like, it looks something like this, and it is symmetrical because you have a plane of symmetry in this molecule, and due to the, like, on the left and right side of this plane of symmetry, you have this molecule symmetrical. So that's why it is called a symmetrical bidentate ligand. Whereas you have an unsymmetrical bidentate ligand, I will represent it as AB. Okay, and example of this is this glycine ligand, and here you have this ligand, and here you cannot divide this molecule into two equal halves, so that's why it is unsymmetrical bidentate ligand. So how to find it out, how to find out the number of geometrical isomer? It is same, that if you find out the like the type, the different number of arrangements, you will find out, and that will give you the number of geometrical isomer. Now how to find out that whether the molecule is having like the molecule is optically active or not? So for that you just have to see, you have to find out the plane of symmetry. So if the molecule is having plane of symmetry, then the molecule will be optically inactive. So this thing you have to keep in mind, that if the molecule is having plane of symmetry, then it is optically inactive. So plane of symmetry should not be there. Okay, so I'll just take example of that. So let's take MAA3. So we have a metal with AA means symmetrical bidentate ligand, and we have three symmetrical bidentate ligands. So if I draw this molecule, so it will look somewhat like this. I have like this. Okay, so I will draw this like this, that okay, so we have this AA like this, then AA like this, and this AA like this. So let's find out the number of geometrical isomers first. So how many combination you can make? So here just the combination is AA and AA. Okay, so one more thing, that you cannot take out one of them, because this is bidentate ligand, so AA should be together. Okay, so number of geometrical isomers, so number of geometrical isomer is equals to 0. There is no geometrical isomer of it, because you just have just one combination, so that's why you don't have any geometrical isomer of it. Now if I talk about the optical isomer, so how you have to find it out, the number of optical isomers? So see, I am drawing this dotted line with the red color. Now it shows that these four ligands are on plane. Okay, so these four are on plane, whereas this A and this A, these two are on axis. So these are your axial ligands, these are on your axial position, whereas these four are on your like on the plane, on single plane. So this is octahedral complex. Now is there any plane which cut this molecule into two equal half? So if you are thinking that we can cut this molecule into equal half by this, that we will pass that plane around this red dotted line. Okay, so taking that as a plane, if I cut this molecule, then it could be cut into two equal half, but that is not possible, because this and this ligands are connected. So you cannot cut the ligands by like half of them. Okay, so for these type of complexes where you have a bidentate ligand attached like this, you do not have any plane of symmetry. So plane of symmetry is not present here. Okay, if plane of symmetry is not present here, then optical active it is, this molecule will be optically active. Okay, and if this molecule is optically active, then it will be having two form, that is one D form and one will be your L form. All right, so if I ask you that how many total stereoisomers are there, so how we will tell? Just count them. Like see, you will be having just one geometrical isomer, and you will be having two form of that, that is one will be like one of geometrical isomer, you don't have any geometrical isomer, so just consider it as 0, and you just have one molecule, and you will be having one D form and one L form. So you are having two stereoisomers. So total number of stereoisomers will be 2, and both of them will be optically active. One will be the D form of that, and one will be the L form of that. Or you can understand it in this way, that you have one of this one of the given complex, and the other one will be, if it is the D form, then other one will be its L form, and if it is the L form, other one will be its D form. So you just have two of them. If I apply a plane like a mirror like this, then I will get another set like this. I'm just drawing over here, so I will be having like this. All right, so it will be somewhat like this. So both will be optically active, both will be mirror images of each other. So in this way you will find out for the for bidentate ligand. All right, so let's talk about this another example, that is MAB3. Okay, so here you have, like, first of all, what you have to do, first of all you have to draw the octahedral complex in the way, in the possible way you have. Then you have to write down the like the possible arrangement. How you will write the opposite one? Just write the opposite one in a bracket. So how you will write? First of all, take this, so it will be having a, okay, then B, because these are opposite, and then AB. So we have one combination like this. And here if you'll see, so you are having AB, then AB and AB. So you are having two possible combinations. So therefore, if I ask you that is it a geometrical isomer, sorry, it is how many geometrical isomers it will be having? So two geometrical isomers. Okay, and if I ask you that how many optical isomers it will be having, so as I told you that these are not in the same plane, these bonds are not in the same plane, so you cannot cut them with any plane. Okay, so you cannot apply any plane on them, so that to cut them into two equal parts. So it does not possess any plane of symmetry. So if it does not, so plane of symmetry is not present. So if plane of symmetry is not present, then optically active. So both of them are optically active. So both of them are optically active. So both of them will show, it will show D form plus L form. It will also show D form plus L form. So how many optical isomers are there? So optical isomers are how many? 4. Okay, and all right. So these are 4 optical isomers. Okay, so let's move on to one more example. Let's take, so let's take, we have MAA whole twice and B2. Okay, so first of all, let's try to draw it. So if I draw, so it will be AA, okay, then BB. I can draw it like this, and one more way I can draw, that is MAA okay, AA and BB. So here what I have done, like these ligands I have taken on the axial and planar position. So if I ask you that how many combination are there, so just check that whether you have drawn it correctly or not. So just check, if both of them will come different, then yeah, you have different combination. So just take the opposite one. So you have AA, then AA, okay, and then BB. So this is one combination, and for this you have BA, you have BA, okay, and you have AA. So you have two type of combinations. So that means you have two geometrical isomers. And if I ask you that how many optical isomers are there, so is this optically active or not? So yeah, it is optically inactive. Sorry, it is having a plane of symmetry. How it is having plane of symmetry? If I cut this molecule like this, so if I cut this like this in this way, so what will happen? These two will be cut into two equal half. So it will have a plane of symmetry will be there. So optically inactive. Okay, so this molecule is optically inactive. Whereas if I talk about this one, and if I ask you that whether it is optically active or not, and if you are thinking that you can draw a plane like this, like something like this, and try to make this molecule optically inactive by making that plane of symmetry, so that is not possible. So the plane of symmetry along this plane is not possible, because these ligands are not in the same plane. One is like they are in different planes, so you cannot cut them in two equal parts. Okay, so whenever you get ligands like this in two different planes, we cannot cut them. Similarly here also we could not have cut them. Similarly here also we cannot cut them in two equal halves. So that's why it is also it does not have plane of symmetry, and it is optically active. Okay, so in this way you can easily find out that whether your complex is optically active or not. Let's take one more last example, and then we will move on to solving questions. Okay, so let's talk about this example that is having MAA B2 C2. So here if I draw the arrangement, I could make them like this, that I can make AA like this, then B like this, and C like this. Alright, so this is one the way, and the second way is like keeping this AA over here. I can just change this B and C. So B and C, I can draw it like this. Okay, so these are the two ways in which you can make them. All right, now if I ask you the arrangement, if I ask you that whether it is optically active or not, so you can draw the geometrical isomers, I think now. But to find it out that whether this is optically active or not, so what you need to find out, how you can check that whether you have the complex is having optical activity or not. You just on the axial position on this straight line, whether you are having same ligands or not. If you are having same ligands on this line, that this will poses a plane of symmetry. Then plane of symmetry will be there and it will be optically inactive. Okay, and if these ligands are not same, okay, so what you have to check then, if these ligands are not same on the straight line, then you need to check, on the both the sides. If both the sides the things are same, then it will possess plane of symmetry. So I'll just summarize the things and I'll just write it. So if you have same ligands, like if you have same ligands on axial position is same, if it is same, okay, then it will possess plane of symmetry will be there and optically inactive. All right, and if these ligands are different, then what you have to do, you have to now check for the second thing, that what, that if the ligands are different, then check on both the sides. If both the side you have same thing, like here also same and here also same, then the plane of symmetry will be there. Okay, so if ligands are different, then go for this, that is whether both the side you are having same thing or not. Okay, so if you have same thing on the both the side, then it will be having plane of symmetry and it will be optically inactive. Okay, and if you have like the ligands on the axial positions are different, and on both the side, if one side you have same but other side you are having different arrangement, then plane of symmetry will not be there and it will be optically active. Similarly, if you are having different both the sides, if you have different arrangement, then also plane of symmetry will not be there and it will be optically active. So these are certain ways in which you can understand and you can find that whether your complex is optically active or not. So one more example I'll tell you and I'll check with the help of the trick. So we have AA2 and BC. Okay, so let's take this example. So if I draw this arrangement, so it will be like this. Okay, so A, then A, then B and C. I can draw it like this, or I can draw it like this. So A, then A, then B and C. Okay, so if I ask you that which of them is optically active, so what you will see, first of all, on the axial line, you have to see that whether on the axial line you have same ligands or not. So here we don't have same ligands, we have different ligands. So now you have to check on the sides of the of this axial line. So on the both the sides the arrangement is same. So arrangement is same on both the sides. So that's why this will possess a plane of symmetry will be there. Okay, and it will be optically inactive. Whereas in this case this will be not have any plane of symmetry. Why? Because these ligands are not axial, like these are on the different planes, so that's why it will not possess any plane of symmetry and it will be optically active. Okay, so this is the simple way of finding out that whether your ligand is optically active or not. So I will just wind up all the things here and I will not go on more examples. You can check on your own that whether you are getting optically active or not, and if you find any difficulty in finding it out, then you can write in the comment section. So I'll just quickly go to the questions which were asked in previous CSNet exam and I'll just solve them. to make you people understand that how to apply all these things in the questions. Okay. Alright, so let's talk about this problem from CSR December 2015 exam, and this question was asked for 4 marks. Okay, so the question says that among the following complexes, so you are given with 1, 2 and 3 complexes. It is asking that the chiral one is, so which one of them is chiral? So alright, so here we are having 3 ligands are given. One is oxalate, that is your bidentate ligand, and here you have ethylene diamine, that is also a bidentate ligand, and then your EDTA is your ethylene diamine tetraacetate, and your hexadentate ligand. So this is your one of the hexadentate ligand, and they are asking that which of them is a chiral one. That means which of them is the chiral ligand, means which of them is a chiral complex. So all right, so we'll talk about them. So first of all, we'll first just find out the structure of the complex. So in the first one, that is oxalate, we have this is called oxalate. Okay, so it looks somewhat like this, and if I talk about the symmetry, whether it is symmetric or not, so if I draw this line like this, okay, so if I just draw a line like this, so it will become a symmetrical oxalate. Okay, so oxalate is a symmetrical bidentate ligand, and similarly EDTA is also a symmetrical, it is not a bidentate, actually it is a hexadentate, because it is having 1, 2, 3, 4, 5 and 6 binding ability. Okay, so it's not a bidentate. EDTA is not a bidentate, whereas ethylene diamine and oxalate both are bidentates. Okay, so let's find out. So first of all, we'll draw the structure of first, that is COOX. So what is this chiral one? What is this chiral means? Chiral compound are those which are not having any plane of symmetry. So if a compound is not having plane of symmetry is not there, then it will be optically, what I told you, optically active, and all optically active compounds are chiral. So chiral compounds are optically active, or optically active compounds are chiral. So this is the relation between all of them. So we'll just, so this is oxalate is of symmetrical kind, so we can just write it out as AA whole thrice. So this is nothing but of the kind of MAA whole thrice. This is something like this. So if I have already told you about this, and again I'll just tell you that if I draw this like this, so AA and AA and then AA. So whether is there any plane of symmetry which can like cut this molecule into 2 equal halves? So there is no plane of symmetry, because these ligands are in different planes. So that's why you cannot cut it into equal halves. So there is no plane of symmetry, and if plane of symmetry is not there, that means the compound is optically active and it is chiral as well. Okay, so this one become chiral. So A1 is your A is the chiral compound. Now talking about the B, so in B you have, this is a bidentate ligand, so here you can write it like this, MAA whole twice. I have written just AN as AA whole twice, and then Cl2. These are monodentate, so I can just write it like this. Okay, so this is something like this, and it is written that it should be trans 1. Trans 1 means the angle between this BB should be how much? 180 degree. So if I draw this like this, so I can draw in two ways. See, I can draw it like this, AA, then AA, and then B. One way of drawing it like this, and other way is like we have already discussed these. So you can draw it like this, BB, then AA and AA. So you can draw this like this in as well. Now which one of them is trans? So trans means that the angle between the two ligands should be 180 degree, whereas here if you'll see, the angle between the two ligands is 90 degrees. So this is not trans, this is the cis form, whereas this one, here you have angle between these two ligands as 180 degrees. So this is your trans. So we have to talk about this one. Now this is of the kind what I have told you, that if on the axial line you have similar ligands on the axial line, that means it poses plane of symmetry is there. So that means if the same ligands are there on the axial line, then this complex is having plane of symmetry, and if it is having plane of symmetry, then it is optically inactive. Okay, and it is, if it is optically inactive, then it is achiral, or like this is not a chiral one. Okay, so this second one is not chiral one. Now if we talk about the third one, so if like the third one, drawing the structure of the third one is little tricky. I cannot draw like like in a simple way over here. But see, it is a hexadentate ligand, and one ligand only is attached from the 6 positions to this chromium, and this whole molecule is not that, like you cannot cut the molecule into 2 equal half. So remember that if you have a hexadentate ligand attached to a metal, that makes the compound achiral. Okay, that means it does not have any plane of symmetry for that. So this thing you have to remember. So for hexadentate ligand, you cannot have, like, plane of symmetry is not there, and this is chiral, and this is optically active. So how many of these complexes will be optically active? So A is optically active and C is optically active. So in the options there were A and B, B and C, A and C. So the option number in which A and C was there, that will be the correct option. So in this way you could have got 4 marks in CSR CSR December 2015. I will take one more question from CSR June 2017. Alright, so we have this question for 4 marks from CSIR June 2017, and the question says that consider the following statement. You have the statement, and you have these 4 statement, and you have for these complexes. So you have these 4 complexes, and the statement says that their DD transition is 14,900, 17,500, 21,800 centimeter inverse. Then second statement says that their spin only magnetic moment are same. Then the third statement says that 2 of them is optically active, and the fourth statement says that they show all of them shows John-Taylor distortion. Okay, and the options are like A, B, C, A, B, D, something like that. You can check the question in the question paper of CSI June 2017, and it was for 4 marks. So maybe question number 71 or what, I don't remember the exact question number. So see, this spin only magnetic moment, that you can calculate. I have already made a video, and I hope that you people understand this concept till now. So I'm not going to solve it over here. I'm just leaving it for you guys, and you have to check this thing, and you have to tell me in the comment section that whether the spin only magnetic moments are same for all of them or not. If it is same, you have to tell me in the comment section. If it is not, then also you have to tell. Okay, so spin only magnetic moment you have to find out, and if you do not know how to find it out, here is the link for that. Okay, I have made a video on that, so here is the link for that. You can click on the link and you can watch that video. Then whether they will show John-Taylor distortion or not, that also I have made a video, and I hope if you people are following my videos, if you people are following me really like with full of your attention, then you people would have you could have, like, you can do this question. Okay, that all of, if they are John-Taylor distortion, they will show John-Taylor distortion or not. So here is the link for that. If you don't know about John-Taylor distortion, if you haven't watched that video, so you can watch it in this link. Okay, so these 2 points I'm leaving for you guys, so you have to do. I will just do this point, that is the point number 3, that is 2 of them is optically active. So I will just do this. So for the first complex, that is CrF6, so fluorine is a monodentate ligand, so it is of kind Ma6. Okay, so it is of kind this. Then second one is chromium and oxalate whole thrice, so it is of kind like metal A whole thrice. Okay, because oxalate is a symmetrical bidentate ligand. Now we have chromium En whole thrice, so here also it is MAA whole thrice. So this both are same, because both are En is also what you call symmetrical bidentate, and oxalate is also symmetrical bidentate. So I told you that to find out the optical activity for Ma6, if you find, so these were of the first kind. So here the number of like the number of possible arrangements are like A, and A. So it will not show any geometrical isomer, but here optical isomers is asked. So there I have told you in the starting of the video that if two like if the ligands are repeated in the pair, then this is optically inactive. Okay, so the first one becomes optically inactive. Now if we talk about the second and third, both are of the same kind. So if any of them like is optically active, then obviously both of them will be called optically active, because both of them are of the same kind. Okay, so if I draw the structure, so I have already discussed about it, yet again I'm just discussing with you guys. So this will be like this. Okay, so all right. So whether there is a plane of symmetry in this molecule, so no plane of symmetry. So plane of symmetry is not present because the ligands are not in the same plane, they are in the different planes, so you cannot cut it with a single plane of symmetry. So no plane of symmetry, that means optically active. So this one also becomes optically active, and this one also. That means B is also optically active and C is also optically active. So yet, yes, this statement becomes true. That is, two of them is optically active. So this statement is correct. Now, it is up to you guys that you have to tell me that whether option statement number is correct or not, and whether statement number D is correct or not. And for statement number 1, where their DD transition is this, like you have different values, so it depends on the the intensity of this ligand, whether it is a strong field or weak field. So strong field ligand will possess more splitting of the d orbital, and this value will increase. So this value will be more if this ethylene is having, like in the spectrochemical series, you just have to check the spectrochemical series, and you just have to check that which of the ligand is strong and which is weak. So if this is the strongest one, then the gapping will be most over here. So if this is the strongest one, you just have to check. Then in the spectrochemical series, if ethylene diamine is the strongest one, then it will be having highest value. If oxalate is less than that, then this will be having lesser value. And if fluorine is least among them, so that will be having least value. So that you can do. So I'm just leaving this question up to you guys. So you have to complete this question for me, okay? So I'm waiting for your answers in the comment section, and this is all for this video. I hope you people like it, and if you like this video, please share it with your friends, and to all of them who haven't subscribed the channel till now, please subscribe it, and I'll be making more and more helpful videos for you guys, and I'll be bringing more good stuffs for your preparation of CSI NET exam. And to all of them who are not following me till now on the Unacademy platform, please follow me there also, because there also I'm making videos at both the platforms, and both videos will be different. And on Unacademy you have one benefit, that I'll be making videos on English and Hindi both, okay? So that is one good thing on Unacademy. So that's all for this video. I hope you people like it, and thank you so much for watching. Have a great day. Bye bye.